Hello guys, welcome back. So last time we were doing residual analysis. So in this video, we'll continue with the analysis and we'll see a few more things. Let me start by sharing my window. Okay, so this was the MATLAB code that we ran and we looked at two models basically. One was kernel maximum core entropy and the other one was a linear model. And we were trying to do regression and we came up with a few numbers for mean square error, and then we tried to find out which model is the best. And again, that's actually a very good problem. You have n number of models out there. You have SVM, random forest, and all those models. Which model to select? And that becomes again a question, a very important question. So what I did was I computed, the error values between my real value and my predicted value, and I stored them in my array. Let's say my array error, and I checked the distribution for error. I ran the model for this KMCC model, and then I ran my code for the linear model. And I computed the error for both the cases, and then I checked their distribution. And when we did that, we got this distribution for the linear model and for the non-linear model. And let's look at this. Now, in this case, for the first case, I told you the distribution of error should look like a normal distribution. Now let's see. Most of the time, see these peaks I'm getting are at around 0 or some 0.0 something, which is not a bad thing at all. The peaks, again, for an ideal case, for when my real value is equal to my predicted value, the error is 0, simple. And that's true, the error is 0. So what we do here is something like this. Let's say you have, let's look at the analysis part. See, we have this, exception, and we have an exception here. Similarly, for this model, we have an exception here, and we have an exception here. Ideally, again, looking at an ideal situation, the error value should be 0. The error value should be 0. In other words, the distribution for an ideal situation should be, a pointy distribution with very little variance, basically. See, I have this spread of data, and here the data is spreading from here to here if we ignore these two values. First of all, see the spread of data here, the error values, and see the spread of error values here if we ignore these two, because these two are clearly outliers. In this case, the MSE value was 0.0159, I think, if I remember that correctly. Similarly, for this case, it was like 0.0089. For an ideal situation, we all know that the error values, this should be the distribution of the error should be like a peaky thing. It should have a peak of something. And the variation, the variation in my error should be less. And that's an ideal case. In fact, let's go to the dream world. Let's go to the La La Land. The distribution of that world would be like this. Single bar centered at around 0. By the way, that doesn't happen. We all know if it's 0, everything is 0. If the error values are 0, that means there is some problem. Because we are working in the real world, we're not in La La Land. But again, that's a theoretical situation. It can happen. It's a theoretical situation. It can happen. The model is so good that it's the real and the predicted values, they are like exactly the same. So the distribution, the entire histogram will be concentrated on error, on 0. But in the real world, these things happen like this or this. So let's look at this. Now, there are a few things that we can, straight away see. First situation, outliers, we can't do anything about outliers because outliers will always be there in the real world. We cannot do anything about outliers. But there are other things that we can do. First thing is, look at the spread. Look at the spread in your error values. The spread should be less. Yes, that's the first, important point. The spread, the variation. In fact, if we go in statistical terms, the variance in the error should be less. That's common sense now, as expected. If there is less variation, that means the error values are concentrated in a particular region. And that's what we want, basically. That's what we want. See here, in this case, all the error values, they are like concentrated in this region. In fact, majority of the error values I can say are in this region. Or let's decrease it even more in this region. Between I don't know, minus 0.18 to plus 1.8 or plus 0.18. But again, in reality, this is not the case. So, but we can see, yeah, here the variation in error is less. Here the variation in error is high. Let's take a look at the real number. What's the variance of error? It's 0.0089 for this case, KMCC case, and let's go to the linear case and let's run it. Real is your y, predicted is your y underscore estimate. Error is real minus predicted. Oh, sorry, I forgot to put a equal sign, and let's check the variance. Error. See, for the previous case, the variance was, again, luckily, let's go to this graph again. The variance of error was 0.0089. Luckily, we got the same number. Whereas for this case, let's see the variance value, its variance of error is 0.151. So that's what I said. Again, the variance in error should be less. Here it's less. Here it's more. And that's again a first sign. That's the first sign. Second sign is, ideally, again, that's what I said. Ideally, again, theoretically, this should be the picture. Real minus predicted is 0. Again, that doesn't happen, by the way. Ideally, we should have a graph like this. Very little variation and a peaky graph. Peaky graph. See, in this situation, we have a peaky graph at around 0. Yeah, at 0, it's like this height is maximum at 0. That means the error value is 0. That's nice. That doesn't happen often, but anyways, it's happening. So that doesn't happen often, but it's happening here. That's nice. Here, the error value is at its peak, at around, I don't know, 0.01 or something, I don't know, the real number. But again, the second thing should be, it should be like peaky thing. There should be, peaks with little variation. Or at that, obviously that doesn't happen. But again, if it's like this, and the data is, the error values are spread nicely. Again, theoretically, that is supposed to happen, but ideally we don't want that. Ideally, we want something like this because we are working on real problems. Of course, it's if we draw a complete distribution over the complete error values, then we get something like, let's take a look at this. Then we get something like this. It's not normal, by the way, because we have got these fat tails. These mean you have a lot of exception, and that is something we don't want. And that's, by the way, a common sense. We don't want outliers in our data. So to conclude from this residual analysis, from this plot, from the distribution of error, The distribution of error should be, first of all, the variance in error should be less. Second, we should try to find a model that gives us this kind of situation, but ideally we don't get it. But again, if a model is giving this situation, then it's the best model. Without a doubt, it's the best model. If we are getting something like this, and in this case, for example, in this case, we saw we have only 2 outliers. In this case, there are so many error values, lying in the tail section. This model again is not that good. It's not the best of models. So we don't want that. And that's how you can visually, inspect which model to select for your data or for your problem. So that's it. Thank you very much for watching. Hope to see you again. Bye-bye.